Okay, so we talked about the fact that we have two types of forces, contact forces and field forces. See if I can scan that in. There, that looks better. And then we did our Newton's laws. One was our object in motion. The second we talked a lot about, and basically we said that net force was going to equal mass times acceleration. And remember that this really is, while it's our most common form, remember it's actually a special case. And the third was forces come in pairs. So we talked about this. Now, this is where life becomes challenging for some of you. Because what happens is, as we work through physics, they say, well, once I figure out what equation to use, I can solve the problem. Well, this is when life gets a little complicated, because this, as simple as this looks, we end up having to deal with and make our own equations. We're always going to be deriving our own equations for the given situation. So for example, I'm going to have a boat in a river here. So we've got a boat in the river or a canal, and we're going to give ourselves a kind of an axis to work with. And if I were going through the Panama Canal, I'd have these little railroad train things, and they call them mules, because on the Erie Canal, it used to be mules. And we would have a tie rope to our mule, and this is applying a force. So we've got a force here. This mule is applying a force. And we've got this force here. So this is force 2, and that's force 1. And we want to know is what is the net force? We want to know the net force on the boat. That's really what we want. So we're going to be given this picture, and we're going to say that that's 35 degrees. We're going to say that this is 40 degrees. And we're going to give our force 2 as 150 newtons. And our force 1, we're going to give it to be 160 newtons. And we want to know the net force. Well, let's take a step back for a second. Remember, we said yesterday that weight was equal to mass times gravity. And we're also saying, and this is what we're doing, we're saying the summation of the forces is going to be our net force. And we didn't clearly articulate that on Wednesday. I was waiting for today to do that. So our sum of our forces, that's what this means. This means sum. Sum of the forces gives me my net force, and we said that that was mass times acceleration. Well, let's look at the units. Mass is in kilograms. Acceleration is in meters per second squared. So I get kilograms meters per second squared, and we're defining that as a Newton. If I'm in the English system, that's a slug foot per second squared, and that is a pound. So pound and newtons are units of force. Now, this is where we get a little discombobulated, because if you go to a scale and you're measuring oranges, and you happen to go to Europe and you're measuring oranges, they'll tell you kilograms. Well, look at this, is we shortcut it because we know that our weight is related to a force, and it doesn't really matter any of the scales that I use. I could put the dial in as a kilogram, because all I would have to do to get my force, my newtons, would be to multiply by the acceleration due to gravity. So we're going back to our boat problem. The first thing you do with these problems is we're going to draw our force diagram, or we're going to draw what we call a free body diagram. You'll see them as force diagrams, you'll see them as free body diagrams, we'll see them as... So we have our boat, and our dot's going to represent our boat. We have our first force. We have force 1 was equal to 160 newtons. We've got our draw here for our reference line, and we showed that that was 35 degrees. We have force 2, and that's 40 degrees. And force 2 was equal to 150 newtons. Now, this now is a vector problem. So we can do this vector problem a couple of different ways. We can imagine sliding our vector here and adding our vector head to tail. And we get this object that's our force parallelogram. In our force parallelogram, and our resultant force, if we look at our force parallelogram, and if I did this correctly and I used my protractor and all of that, I'd end up with this being the resultant force. I'm going to go ahead and draw my parallelogram to make it work this way. And that's our resultant force. And I'm going to boldly put on this note, not to scale. That is not to scale, because that's just for representation purposes. But that's one way I can graphically add my vectors head to tail, because remember, we've been working with vectors for a while. So basically what we need to do is we need to put our vectors into vector form. All right. So my first vector, force 1, is equal to 160 newtons. We have its x component, and we have its y component. And we can write our force 1 vector in its vector notation as 160 newtons cosine, and we said that was 35 degrees, 160 newtons cosine 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 35 degrees, 160 n in the I direction plus 160 newtons sine 35 degrees in the J direction. And if I do that calculation, this is 131.1 newtons. And this is 91.8 newtons. I'm going to do the same thing for my second vector. Force 2. This is my y component. It's my x component. And that was 40 degrees. So my force 2 vector is, and that one was 150 newtons. My force 2 vector is 150 newtons cosine 40 degrees in the I direction, but it's going to be a minus 150 newtons sine 40 degrees in the J direction. So I'm going to do that calculation. And this is 114.9. And this one is 96.4. And those are in newtons. So now I'm going to write out my vectors. This is 131.1 in the I direction plus 91.8 in the J direction, and those are in newtons. My force 2 is equal to 114.9 in the I direction minus 96.4 in the J direction, and that's in newtons. So my resultant force is going to equal 246 in the I direction minus 4.6 in the J direction. So if I want to draw that vector, we know we're going to get a resultant vector that's going to be looking like this, because we know that this side is 4.6 in the downward direction, and this side is 246 in the positive direction. So I can calculate the magnitude of my vector. This gives me 246.04, so approximately 246 newtons. But my angle is going to be the tangent of the angle is going to be my y component divided by my x component. And that would be a negative. So the angle is going to equal a negative 1.07 degrees. So this angle right here is 1.07 degrees. And that's the resultant force on our boat. Now, so now we've got the sum of the forces. So our sum of our forces is going to look like 246I minus 4.6J, but that's also equal to the mass times the acceleration. If the boat had a mass, if the boat has a mass of, we're going to give it 1,600 kilograms, what is the acceleration? Well, that's easy enough. The sum of my forces is equal to 246I minus 4.6J, which is equal to mass times acceleration. Or if I do this, the sum of my forces divided by mass is equal to the acceleration. So I can have 246 divided by my 1,600 kilograms. And this is in newtons, and that's in the I direction. And then I just divide by the J in the J direction. And that's going to equal my acceleration vector. Let's do the unit analysis first. So newtons divided by kilograms is equal to a kilogram meter per second squared divided by kilograms. And that just gives me meters per second squared, which is an acceleration. So I've done everything correctly. So now I take my 246, divide by 1,600. And that gives me my 0.154 meters per second squared in the I direction minus 0.003 meters per second squared in the J direction. Now, one of the things that we know is that this force vector here, the acceleration vector, is in the same direction. So whatever the resultant, the net force is, the acceleration vector is going to be the same direction as our net force. So we already know the direction. So now we just want to calculate the magnitude, just so that we have the magnitude of our acceleration. And that's going to be the square root That's going to give me 0.154 in the meters per second squared. But we could have done the same thing because we had our resultant vector, right? Our resultant vector is this. On the magnitude of our resultant vector, that was the force, that was 246 newtons. So if I take the magnitude of that resultant vector divided by the mass, that's going to give me the magnitude of my acceleration vector. And that's going to give me 246 divided by 1600. And that's this is kilograms, meters per second squared divided by kilograms gives me meters per second squared. And I get 0.154 meters per second squared. Okay. So we have an object on the table. And it has a mass of 10 kilograms. We want to know what is the force on the object applied by the table. So this gets us into our idea of our normal force, which we introduced on Wednesday. But remember our Newton's law. So the first one is an object in motion remains in motion, or an object at rest remains at rest. We also have the second law says that the sum of our forces, now we're going to write it in our shorthand, is mass times our acceleration. And the third one says forces come in pairs. Okay, so if I have an object sitting on the table, first thing that we know is it's at rest. So our sum of our forces, which is mass times acceleration, has to equal 0 because there's no motion. Because there's no acceleration, this thing is at rest, there's no net force. Or that the net force is equal to 0. Okay? And we mentioned it, we said that that was our first condition of static equilibrium. Now we know, so now we're going to draw our free body diagram. This is our force due to gravity. And then because of the third law, we have an equal but opposite. We have an equal but opposite force, and this is the force by the table to the object. And we said our force due to gravity is the weight. Which means that that's mass times our acceleration. And that's going to be 10 kilograms times 9.81 meters per second squared. And that's going to be 98.1 newtons. This equal but opposite force, we're calling the normal force. So that equal but opposite force is our normal force, and we've got that. Now, one of the things we showed on Wednesday is that we talked about trying to get this object to move. We're going to try to get this object to move. So if I apply a push to get this object to move, one of the things is if I apply a push this way, so if I apply this push, the object's not going to move, because what's going to happen is the table is going to resist that push, and all I'm doing is increasing the normal force. So if I'm trying to get this object to move and I apply a push, all that's going to do is now if I apply a push, I come over here, and now that's my other force that's on here, and that's my push, still not moving. So if I write the sum of my forces, we're going to write the sum of my forces. My forces are going to equal the normal force in the upward direction minus the push minus the weight. So if I'm applying a push here, just like this picture, and I've drawn my free body diagram, I can write my sum of my forces, which is going to equal my net force. But guess what happens? This isn't moving. So if I have no motion, that has to equal 0. So basically what that's saying is that my normal force now is equal to the push plus the weight. So my normal force is equal to the push plus the weight. So that's kind of entertaining. But let's talk about the push in a different direction. So now I'm going to have an object on the floor. We're going to give it a mass is equal to 10 kilograms. So we can calculate the weight. The weight is 10 kilograms, 9.81 meters per second squared. So that's going to be 98.1 newtons. So I can draw my free body diagram. There's my force due to gravity. There's my normal force. And I can use an N, or you'll see a little n. A lot of times you'll see a little n so it doesn't get confused with newtons. And so we know, and so now we can calculate the normal force. That's the sum of the forces. Now this is interesting because these forces here are in the y direction. I'm still going to have independent motion so I can have some of the forces in the X direction, some of the forces in the Y direction, and the sum of the forces in the Z direction. So right now, I've only got forces in the Y direction. But now I'm going to apply a push. My push is going to create an unbalanced force. My push is going to create an unbalanced force. So the motion that I'm going to get will be in the same direction as my push, which right now is only represented as a Y only or an X only component in that image. That right now it's only as an X only component. And if there's no friction, we know that the sum of the forces in the X direction is going to equal the push in the X direction. But if I have friction, friction applies another force. My friction is applying another force that's resisting the movement. So now I've got to add that. So if I've got friction, so now my free body diagram would look like this. I've got my normal force. I have my force due to gravity. I have my push. And then I have a resistive force that we're going to call my force due to friction. And we're going to use a script F for my force due to friction. Now it turns out that my force due to friction, the magnitude of that force due to friction is going to equal the coefficient of friction times my normal force. This gives us the friction is spun t-shirts. Because that's how you remember that equation. So the magnitude of my force due to friction is going to equal the coefficient of friction times the normal force. And this can be a static friction. And so the force due to friction that's based on static friction has to be overcome. To get it to move. Now my force due the coefficient of kinetic friction is the resistive force the resistive force based upon the material. And it's while moving. So now I got my block with my force due to friction. And we talked about on Wednesday that I can draw these items. I have my inclined plane. And I'm going to draw my free body diagram. There's my gravity. My normal force is going to be the force that is resisting, or the force applied by the table onto the block. And that force is going to be perpendicular. And then if I have a force due to friction, it's going to be holding it up. So my free body diagram is going to look like this. This is my normal force, my force due to friction, and my force due to gravity. But what I'm going to do to help solve my problem here is I'm going to create a coordinate system that's parallel to my plane, or perpendicular to the plane. And then I can break these components out. This is my force due to gravity, perpendicular to the plane. This one is my force due to gravity, parallel to the plane. And that's going to also be equal to the magnitude of that is going to be equal to the magnitude of my normal force. Because if we slide a block down the plane, it's like sliding a block over across the road. I'm not necessarily getting anything that's associated with it. Now, if I write my angle, and we talked about this on Wednesday, that angle and that angle are the same. So now I would have the sum of the forces perpendicular to the plane, which is going to be my normal force, minus the force due to gravity, parallel, which is equal to, or perpendicular, which is equal to 0, because I'm not falling through the plane or anything like that. So my normal force is going to equal FG cosine of my angle, because this is the adjacent side. Now the sum of the forces perpendicular to the plane is going to be my frictional force minus my force due to gravity parallel. Oops, did I do this? I did this wrong. This is perpendicular, and that's parallel. It's like, what the heck? Force due to gravity parallel. If not moving, that's going to be 0. If moving, this is going to equal mass times my acceleration. So we can determine the coefficient of static friction by sliding blocks down an inclined plane. So just before a block moves, the fraction of a second before a block moves, and we measure this angle, so we're going to measure that angle as 25 degrees. At that precise instant, F minus FG parallel has got to equal 0. If we have this block has a mass, we'll have the block have a mass of 5 kilograms. The force due to friction is going to equal the force due to gravity parallel. That equals mass times gravity times the sine of the angle. That equals, this equals the coefficient of friction times my normal force. But the coefficient of friction times my normal force is equal to the coefficient of friction mg cosine of theta. So that equals mg sine of theta. My coefficient of friction is going to equal mg sine of theta divided by mg cosine of theta, which is equal to, that cancels, that cancels, that actually equals the tangent of theta, or you can just calculate it out. But now I can actually calculate a coefficient of friction based on an inclined plane by looking at the various components or frictional components. So let's work a problem here. We're going to make this 40 degrees. We're going to give ourselves a distance of 10 meters. We're going to give ourselves a coefficient of kinetic friction is equal to 0.25. We're given the mass of my object. Mass of the object is going to be 10 kilograms. We want to know what the velocity is when it reaches the bottom of our inclined plane. Okay. Remember, velocity final is equal to velocity initial plus my acceleration times time, or my velocity final is equal to velocity initial squared plus 2 times the acceleration times my change in x. I need acceleration to solve this problem. But I now have another way of doing it. We know that the sum of the forces parallel to the inclined plane is going to equal the mass times acceleration. Now, if we draw our free body diagram on here, we've got a force due to friction, and we've got a force due to gravity parallel to our inclined plane. We know where our weight is, right? So we know this, and that force is going to be that angle here. So I'm going to be mg sine of my angle. So this gives me my force due to friction minus my Fg parallel. We have to figure out our force due to friction, and the force due to friction is going to come from our force perpendicular. Which is going to be mg cosine of theta. No, I did this wrong. That's my normal force minus my force due to perpendicular. So the normal force is equal to my force due to perpendicular, which is equal to that. Sorry. Okay, so I've got my force due to friction minus my force due to gravity parallel is equal to my mass times my acceleration. My force due to friction is my coefficient of kinetic friction, mg cosine of theta, minus mg sine of theta is equal to ma. My acceleration is going to be the cosine of the angle minus gravity sine of the angle is equal to my acceleration. And now I can plug in numbers. I get 0.25 times 9.81 meters per second squared. Cosine of 40 degrees minus 9.81 sine of 40 degrees is equal to my acceleration. And if I punched it into the calculator correctly, I get my acceleration is equal to a negative 4.43 meters per second squared. And that's parallel to my inclined plane. And if we start this at 0, our initial velocity is 0, we get v final squared is equal to 2 minus 4.43 meters per second squared. And we're going down the plane, so that's a negative right there. So I get v final squared is equal to 88.5 meters squared second squared. V final equals 9.4 meters per second. And I'm gonna